Okay, just are about to the end of our discussion and work in class related to kinetics and mechanisms, and I just want to touch on a few finishing points related to this, and then we'll be moving on to other topics related into the course and kinetics and so forth. But first, I want to just remind you about three ways to solve reaction systems. So we've basically gone over three different ways to do this, and depending on the complexity of the system and the information we know, we may use one of these different ways. The first one is approximation, and most common approximation is the steady state approximation. In this case, this allows us to make some simplifications on our system and basically turn a differential equation problem into a much simpler algebra-like problem. It's valid for steady state, which is great if we are trying to run this in, say, reaction conditions in a factory or whatnot. But for that transient conditions where the concentrations may be changing with time, it may not necessarily be a good approximation, but usually it is, depending on the system we're studying. So that's one, is the steady state approximation or other approximations. We'll talk maybe a little bit about one of those. The other is solving differential equations, ODEs, analytically or exactly. And this is feasible if we have some differential equations that we know the solutions to, and this is what mathematicians and so forth, they spend their time doing, is coming up with solutions to differential equations. And if we can look it up in a table or a book, or we can use some sort of mathematical software to solve it analytically, great. And the other one is ODEs numerically, and this is really probably more realistic way to solve a series of differential equations, especially when we get a large number of differential equations. And if we have 10, 20, 30, 40 reactions going on, the number of differential equations is pretty large. And so solving it numerically is much, much easier analytically when we get to these very complex systems. So those are the general ways in which we go ahead and solve reaction systems. Now let me just pose or bring up another issue related to this, but what about partial differential equations? So do we have to worry about these? Is this something? If you're scratching your head and saying, what's the difference between partial differential and ordinary differential, just to remind you, an ordinary differential equation has a derivative with respect to one variable. So dy with respect to x is equal to x squared. That is a ordinary differential equations. Now if we had dy dt plus dy dx is equal to x times t, that would be a partial differential equation, because now we have it a differential equation that has two different variables. It depends on two different variables there, or at least it contains a multiple variables, but it has derivatives with respect to multiple variables. So that's what we're interested in, is when do we have to worry about this case right here? Well, for the most part, when we're dealing with kinetics studies, ideal kinetic studies, we don't. And the reason is because we're dealing with well-mixed, homogeneous solutions. So if I have a reactor, and I'm just going to do a good old plug flow reactor, assuming that it's well mixed within the radial direction, that is, the concentration is the same no matter how far we are from the middle of our reactor, then we don't have any sort of inhomogeneities. But on the other hand, if there is a concentration gradient from the center of our reactor to the walls of our reactor, that's when we have to worry about using an equation like this, a partial differential, where we have a dependence not only on the time or length along this direction, but we also have a dependence along the radial direction. And the same thing goes if we have a batch reactor. If there is a concentration, there's maybe a concentration here in the middle and a different concentration on the edges, then we will have a gradient of the concentration with respect to distance from the center or whatnot. So that way we might have these partial differential equations. Ideally, we don't want to have to worry about that. We want well-mixed systems where there's no concentration gradient and the concentration is uniform throughout. And so in that case, these ordinary differential equations are really what we have to worry about. And in this class, we're not going to really worry too much about partial differential equations. Maybe in reactor design class that might be appropriate, but not so much in this class. Okay, so we have all these methods that we've developed, and we have a particular reaction we're interested in, or a bunch of reactions, and we want to go ahead and analyze it and predict what's actually going on within our reactor. And this is where mechanism analysis and kinetic analysis comes into play. But how do we go about actually understanding what's really going on within a reaction? Because again, a real reaction system may contain hundreds to even thousands of reactions taking place. The systems we've been looking at have been pretty simple, 3, 4, 5 reactions maximum, but again, a real system may have many more. And this is where reaction and mechanism analysis comes into play. And so a very simple way to test a mechanism, and let me just write this out here, is to guess a mechanism. So let's go ahead and guess a mechanism for a bunch of a reaction that we're interested in. Determine rate equations. So all this we've already done. Similar work, determine rate equations from that mechanism. Then after we have the rate equations, either we do it before or during whatever reaction data, we measure the reaction data. Then we go ahead and ask the question, does our rate equation or rate equations fit the data? And we've done this before. We've fit our data to reaction expressions or reaction rate equations. If it does, great. If it doesn't, modify the mechanism and repeat. So come up with a new rate expression based off of a new mechanism. And that's the general idea behind going about trying to analyze a system. And if we're lucky, then we might have some data about some of the elementary steps based on other tools, spectroscopic tools that tell us what intermediates may be present in our system, so we know that the mechanism must have those intermediates. But if we have that, great. Now let me just say this right here, that this is all well and fine and dandy and so forth, but just because you have a mechanism that fits data does not mean that you know the actual reaction mechanism. And let me just give you an example. Let me just box this here. The reaction, an HI reaction. So the HI reaction, now people have studied a reaction between hydrogen and iodine to form HI, and various different mechanisms have been postulated. So let me just throw these out at you. First one, H2 plus I2, going to form some sort of forming HI through some sort of intermediate like this, some reaction intermediate. So we have some sort of bonds forming between hydrogen and iodine such like this. So this is some sort of transition state that's been proposed. Another mechanism involves iodine interacting with some sort of catalyst or precursor to produce iodine in a activated state. And this activated iodine is able to break apart into iodine atoms. And then these iodine atoms, here's a side reaction, but H2 plus 2I forms 2HI. So this is different than the first mechanism. This first mechanism has hydrogen, molecular hydrogen and molecular iodine interacting directly with each other. In this case, the reaction is driven by atomic iodine interacting with molecular hydrogen. And there's still a third mechanism that's been proposed. and where we have similar activation of iodine to this activated state, and then this activated iodine forms atomic iodine, and then we have the side reaction. Side reaction here of basically the reverse of iodine, molecular iodine breaking apart. In this case, we have one iodine atom interacting with a hydrogen molecule. And then finally, atomic iodine interacting with this IH2 species to form our HI atoms. Now these are three different mechanisms that have been proposed, and the interesting fact is that all three of these mechanisms can fit the data very well, the reaction data. So people have studied this reaction, and they've proposed three different mechanisms, and all three mechanisms seem to fit the data reasonably well. So just doing the mechanisms and coming up with rate expressions is not alone sufficient to tell you exactly what the mechanism is. And this is where we're relying, as I said, on other tools. For instance, if I had spectroscopic tools, I may be able to detect whether this species, this IH2 species, really is present in the reaction when it's taking place. Because if it is, then that tells me that maybe this reaction mechanism number 3 is actually the one that's taking place. On the other hand, if I can identify, or if I can show that it's this IH2 species is not present, then that would potentially eliminate this mechanism. So again, we just have to be careful, and cautious when we're defining mechanisms or trying to explain what the mechanism is. Okay, one final topic here today, and that is the rate determining step. So we have talked about the steady state approximation, and which is a way that we can eliminate some of our variables and simplify our reaction equations to come up with some equations that are actually easier to solve. There's another approach, which is the rate determining step approach. And the idea behind this, let me just write out a bunch of reactions. If we have this reaction system here, and I could just keep going and going. If I have a bunch of reactions taking place, it may be that one of those reactions is slower than the rest. So let's just say E going to F. We'll call this the slow reaction. Because this reaction is so slow, basically this reaction right here, this is the bottleneck. This is the one that controls the speed of how fast this overall reaction goes. This is the rate determining reaction. This one right here, rate determining reaction, RDS. And because it's the rate determining step or rate determining reaction, it's the step that again controls how fast things go. So if we're using the rate determining step approximation, what we do is we assume that all of these different steps that are not the rate determining step are in equilibrium with each other. So in this case, we could say K1, and let me put a bar over this to signify that this is an equilibrium constant, not a rate constant, is equal to B over A, K2, and again I'm going to put a bar, and that's C over B, etc. So we can have these equations, rather than having differential equations that explain this reaction, we now have these equilibrium equation right here. So it makes the math a lot easier. So in actuality, we'll be left with one differential equation. We'll be left with a differential equation for this step, and then all the previous reactions will be simply defined by these equilibrium equations right here. And so the analysis becomes a lot easier because again we only have one differential equation to worry about in our analysis. So that's the rate determining step approximation, and there you go. So just to summarize, There are different techniques that we can use to study and analyze a set of a proposed mechanism and so forth. We just have to take care and be careful when we're analyzing them.